Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we covered trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with graphs of the trigonometric functions. The unit circle gave cosine and sine their definitions, but a definition only describes a single point at a single angle. Plotting those coordinates against the angle across a full horizontal axis produces a shape, and that shape turns out to be a wave. This is the moment trigonometry stops being about triangles and becomes the mathematics of everything that repeats. The sine and cosine curves. Imagine the unit circle to your left and a horizontal theta axis stretching to your right. As point P rotates counterclockwise from the coordinates 1, 0, plot its y-coordinate, which is sine of theta, against the angle on that horizontal axis. Animation 9. A unit circle sits on the left of the canvas. A point P starts at the coordinates 1, 0, and begins to rotate counterclockwise. As P rotates, a horizontal thread connects it to a tracing dot on the right. The dot climbs and falls, drawing the sine curve in real time. The completed sine curve, starting at 0, rising to a peak of 1 at theta, equals pi over 2, returning to 0 at pi, dipping to negative 1 at 3, pi over 2, and back to 0 at 2 pi. The cosine curve traces the x-coordinate of P instead, the same smooth wave shape, but shifted left by pi over 2. Cosine starts at height 1 when theta equals 0, descends to 0 at pi over 2, reaches negative 1 at pi, returns to 0 at 3 pi over 2, and is back to 1 at 2 pi. Both curves share the same three fundamental properties: amplitude 1, period 2 pi, and range from negative 1 to 1. Figure 23. The sine and cosine functions plotted on the same axis over two full periods, from negative 2 pi to 2 pi. The sine curve, solid navy, passes through the origin and rises first. The cosine curve, dashed amber, starts at height 1. The two curves are identical in shape. Cosine is sine shifted left by pi over 2. Two symmetry properties follow directly from the unit circle picture. Sine is an odd function. Sine of negative theta equals negative sine of theta. Reflecting an angle across the x-axis sends the unit circle point from x, y to x, negative y, negating the y-coordinate and therefore the sine. Cosine is an even function. Cosine of negative theta equals cosine of theta. The same reflection leaves the x-coordinate unchanged, so the cosine value is unchanged. Both functions are bounded between negative 1 and 1. No point on the unit circle is ever more than 1 unit from the origin. Worked example: solving a sinusoidal equation. Find all values of x in the interval, from 0 to 2 pi, not including 2 pi, that satisfy sine of x equals the square root of 3 over 2. Identify the reference angle by recognizing the square root of 3 over 2 from the 30-60-90 special triangle. Sine of pi over 3 equals the square root of 3 over 2, so the reference angle is pi over 3. Sine is positive in quadrant 1, and there the angle equals the reference angle. So x equals pi over 3 is the first solution, in quadrant 1. Sine is also positive in quadrant 2. A second solution exists there, with the same reference angle. That second solution is x equals pi minus pi over 3, which equals 2 pi over 3. In quadrants 3 and 4, sine is negative, so there are no further solutions in the interval. The complete solution set is pi over 3 and 2 pi over 3. Try it. Solve a sinusoidal equation. Find all values of x in the interval from 0 to 2 pi, not including 2 pi. that satisfy sine of x equals negative 1/2. Identify the reference angle, decide which quadrants have negative sign, and write both solutions. Pause the video now and give it a try. The tangent curve and its asymptotes. The tangent function is defined as tangent of theta equals sine of theta over cosine of theta, so it inherits all of sine and cosine's behavior, but with a twist. Whenever cosine of theta equals 0, the denominator vanishes and the tangent is undefined. Cosine equals 0 at every odd multiple of pi over 2, at plus and minus pi over 2, plus and minus 3 pi over 2, plus and minus 5 pi over 2, and so on. At each of these values, the tangent graph has a vertical asymptote. As theta approaches pi over 2 from below, sine of theta is near 1, while cosine of theta shrinks towards 0 from the positive side, so their ratio shoots to positive infinity. Just past pi over 2, cosine becomes negative, so tangent jumps to negative infinity and climbs again through the next branch. Animation 10. The tangent curve is drawn from left to right. Dashed vertical lines mark the asymptotes at theta equals plus and minus pi over 2. As theta nears pi over 2 from below, the curve shoots upward to positive infinity. Just past the asymptote, a new branch emerges from negative infinity and climbs again. The full tangent graph over 3 periods, each branch identical in shape, separated by asymptotes spaced pi apart. Figure 24. The tangent function plotted over 3 periods. Dashed vertical lines mark asymptotes at odd multiples of pi over 2. The curve crosses 0 at every integer multiple of pi. Each branch climbs continuously from negative infinity to positive infinity, crossing 0 at the midpoint between asymptotes, so tangent's range is the entire set of real numbers, with every value attained once in each period. The tangent has period pi, not 2 pi, because the sine pattern of sine theta and cosine theta together repeats every pi units. Whatever signs they have at theta, they have opposite signs at theta plus pi, so the ratio is the same. The reciprocal functions secant and cosecant also have vertical asymptotes, occurring wherever their parent function, cosine or sine, equals 0. Try it. Sketch the tangent graph. Sketch the graph of y equals tangent x over the interval from negative pi to pi. Mark the vertical asymptotes, the zeros, and the points where tangent x equals positive 1 and negative 1. Pause the video now and give it a try. Amplitude, period, and phase shift. In practice, most sinusoidal functions you will meet are not the plane sine or cosine. They are stretched vertically, compressed or expanded horizontally, slid left or right, and shifted up or down. And all 4 transformations are captured by a single standard form. Equation 13, the standard sinusoidal form, y equals a times sine of b times the quantity x minus c plus d. The 4 parameters a, b, c, and d each control one distinct visual feature of the curve. The 4 parameters of the standard sinusoidal form. First, the absolute value of a is the amplitude, half the vertical distance between the maximum and minimum. Second, 2 pi over the absolute value of b is the period, the horizontal distance for one complete cycle. Third, c is the phase shift, how far right for positive c, how far left for negative c. And fourth, d is the vertical shift. The midline sits at y equals d. Animation 11. A plane y equals sine x curve is displayed. Slider a increases from 1 to 3, stretching the curve vertically. The amplitude triples, peaks reach 3, troughs reach -3. Slider B increases from 1 to 2, compressing the curve horizontally. The period halves from 2 pi to pi. Slider C moves to pi over 4, sliding the entire curve to the right. The shape is unchanged, only its horizontal position shifts. Slider D moves to 1, lifting the entire curve upward. The midline rises from y equals 0 to y equals 1. Figure 25. A transformed sine curve. Y equals 3 sine of 2 times the quantity x minus pi over 4 plus 1, plotted alongside the basic sine curve with all 4 parameters labeled. Compared to y equals sine x, the amplitude is tripled to 3, the period is halved to pi, the curve is shifted pi over 4 to the right, and the midline is raised to y equals 1. Worked example. Reading a sinusoidal graph. A sinusoidal function reaches a maximum value of 7 and a minimum value of -1. It completes one full cycle every 4 units of x, and its first maximum to the right of x equals 0 occurs at x equals 1. Write a formula for this function in the standard sinusoidal form. Find the amplitude from the maximum and minimum values. A equals max minus min over 2. 7 minus -1 equals 8. 8 over 2 equals 4. So the amplitude is 4. Find the vertical shift. The average of the maximum and minimum is the midline height. D equals max plus min over 2. 7 plus -1 equals 6. 6 over 2 equals 3. So the midline is at y equals 3. Find b from the given period of 4 units. 2 pi over the absolute value of b equals 4. Solving gives b equals 2 pi over 4, which simplifies to pi over 2. Find the phase shift c by locating where the first maximum occurs. A plane sine curve with period 4 reaches its first maximum at x equal to 1/4 period, which is 1. The given maximum also falls at x equals 1, so the curve needs no horizontal shift. Therefore, c equals 0. The function is y equals 4 sine of pi over 2 times x plus 3. Try it. Identify the parameters. For the function y equals 2, cosine of pi times the quantity x minus 1 minus 3, identify the amplitude, period, phase shift, and vertical shift. Then sketch one full period of the graph, marking the midline, maximum, and minimum. Pause the video now and give it a try. A repeating natural phenomenon, daily temperature, ocean tide, breathing rate, alternating current, can almost always be modeled by the standard sinusoidal form. What does each of the 4 parameters tell you, physically, about the phenomenon? Why is the sinusoidal form so universal in nature? That wraps up graphs of the trigonometric functions. Next up, Section 6, Identities. If you found this helpful, like and subscribe and support the channel.